total change and the fundamental theorem of calculus. So all the work that we've been doing up until this point in this section about area under the curve has been leading us up to something called the fundamental theorem of calculus. So the fundamental theorem of calculus tells us that if f prime of x is a continuous function on some interval a to b, then if you were to integrate that derivative function over the interval a to b, that would give you the total change in the original function between those 2 points. I want you to think about the examples that we started with. When we integrated the velocity, which is the derivative of position, over 2 points, that told us the total change of the position function. So we are able to use the derivative to talk about how the original function changed. We can also write total change as f of b minus f of a without the derivative. Again, think about position. If we had the position function, we could plug in the position at time b minus the position at time a, and that would also give us how much the position changed. So now we're able to write down a distinct relationship that equates both the derivative function and the original function. Before, we were taking the integral of the derivative and we were spitting out a number. But now we're writing it as functions. And this becomes really powerful because if we have information about the original function, we can find out even more than we were able to just using the derivative. So again, the definite integral of the derivative of a function gives the total change in the function. So let's look at some examples and see how we apply the fundamental theorem of calculus to a whole lot of situations. Example 1. Suppose ice is forming on a pond at a rate of dy dt equals the square root of t over 2 inches per hour. If y represents the thickness of the ice in inches at time t in hours since the ice started forming, estimate the thickness of the ice after 5 hours. So here, dy dt, that's y prime. So that is going to be what we're integrating. That's the rate that we're interested in integrating. And we're looking at what's happened over the first 5 hours. So that's time equals 0 to time equals 5. So if we integrate our rate, square root of t over 2 dt, the fundamental theorem says that that's going to give us the total change in thickness between time equals 0 and time equals 5. So we can write that as y of 5 minus y of 0. So some of the pieces of how we use the fundamental theorem are the same as what we were doing before. So here we can compute this definite integral using our calculator. And if we plug everything in, we're going to get 3.726. Now let's talk about the units here. So the rate was in inches per hour, and then time, which we have on the bounds, was in hours. So inches per hour times hours, the hours units are going to cancel, and I get 3.726 inches. So that's going to be the thickness at time 5 minus the thickness at time 0. What this question is actually asking for is the thickness at time 5. So I want to take this thickness at time 0 and I want to add it over. So that means I have y of 0 plus 3.726 equals y of 5. So that means that if I had some sort of initial data about the thickness of the ice, that I would add it to the total change, right? Because again, this is how much my function changed, my thickness function. So here the question is, do I know the thickness of the ice at time 0? Now, it's very reasonable here to assume that at time equals 0, the thickness was 0 because we're talking about when ice started forming. So since we can assume that initially that was 0, that tells me that y of 5 will have to be 3.726 inches. So the thickness of the ice at time equals 5 is just as 3.726. However, if my example had told me something like initially the ice was 4 inches thick, or initially the ice was 12 inches thick when we started measuring, then my y of 0 would be a different number, and I would be able to get the exact thickness at 5 hours instead of just how much the thickness changed. So we're able to use initial data to help us understand the situation and to find exact values of the original function instead of just how much the original function changed. So let's look at an example where our initial amount is not 0. Example 2. A cup of coffee at 90 degrees Celsius is put into a 20 degrees Celsius room when time equals 0. The coffee's temperature is changing at a rate of R of t equals -7 to the 0.9 t degrees Celsius per minute with t in minutes. Estimate the coffee's temperature when t equals 10. So t equals 10 is going to be 10 minutes after the coffee has been placed in the room. So if we were to integrate this rate from 0 to 10, what that's going to tell us is the change in temperature over this 10 minutes. And I know from the fundamental theorem that that's going to give me the temperature, let's call that capital R, at time 10 minus the temperature at time 0. So what I'm interested in is the temperature at time 10. That's what I want. I want the exact temperature. So if I were to integrate this rate, this function here, again, I'm going to use my calculator, and that's going to tell me how much the temperature changed. So here, if I integrate that, I get -43.27. So let's talk real quick about units. So the units here of my function were in degrees per minute. My independent units on the bounds here were in minutes. So degrees per minute times minutes. The minutes are going to cancel. So this is -43.27 degrees Celsius. So that's going to be equal to the temperature at time 10 minus the temperature at time 0. So that's the piece we need to figure out. What was our initial temperature of this coffee? So if you look at the first sentence here, we have two pieces of information, and we need to look at them carefully to determine which one is our capital R of 0, our temperature at time 0. So the cup of coffee is 90 degrees Celsius, and the room is 20 degrees Celsius. But what we're talking about in this scenario is the temperature of the coffee, which means that this 90 degrees Celsius is the starting temperature of this coffee. So now I have that the temperature of the coffee at time 10 minus 90 degrees Celsius, our starting coffee temperature. So what we're going to do is we're going to add 90 over to the other side so that we have solved for R of 10. So the temperature at time 10 is going to be 90 plus 43.27. So if we add the 90 over, remember we got to add it because it's subtracted on the right. So when we add that over, we're going to get 46.73 degrees. So the temperature of the coffee at time equals 10 is 46.73 degrees Celsius. And so again, earlier, before the fundamental theorem, I was able to tell how much the temperature changed. So it changed by 43.27 degrees. However, I needed the fundamental theorem to incorporate this initial data, which allowed me to find out the exact value of my function, which is the temperature function, at time equals 10. Let's look at another example. Example 3. The figure below shows the rate of change of the quantity of water in a water tower in liters per day during the month of April. If the tower had 12,000 liters of water, that seems important, on April 1st, estimate the quantity of water in the tower on April 30th. So there's a lot of information here, and then we have a picture that's telling us the rate at which the water is changing. Let's give these functions a name to help us understand what we're doing here. So let's call this Q prime of t, so the derivative of quantity, the rate at which the water quantity is changing. So we know that we're interested in what's happening from April 1st to April 30th. So from time equals 0 to time equals 30, where that represents the days in April. We know that we want to find the area under the curve here. So we're going to find the definite integral for how much the water has changed. And we know from the fundamental theorem that that's going to be the quantity of the water on day 30 minus the quantity of the water on day 0. So what information do we have? What information do we need to find? And what are we actually trying to solve for? So we want to estimate the quantity of the water on day 30. So this is what we're trying to solve for. So if we're trying to solve for Q of 30, that means that we should be able to find values for our integral and our initial quantity. So I'm going to say that Q of 0 is probably the easier piece to find here because that's going to come right from the problem. It says that if the tower had 12,000 liters of water on April 1st, so April 1st is when we started measuring. So the quantity on April 1st is 12,000 liters. So that was our initial quantity, our Q of 0. Now, the change in liters here, how much the quantity changes, we're going to have to use the graph to estimate. So here, we're interested in the area under the curve from 0 to 30. So I want you to remember that any area that's below the x-axis is going to be negative, which means that the quantity was decreasing, and anything above the x-axis is going to be positive. So that would mean that the quantity was increasing. So let's start with the area that's below. So notice that from day 0 to day 12, we have area below the x-axis. So that looks like we're losing water. So if I'm estimating this area, this looks pretty close to a triangle here. So I'm going to use triangles to estimate the area under the curve because it's pretty close. So when I do that, I'm going to do 1/2 base times height. My base here is 12 units long, and then my height is -50. So if I multiply all of those things together, I get -300. And again, it's negative because it's below the x-axis. So that means that from day 0 to day 12, I lost 300 liters of water. And remember, the rate is liters per day, and I'm multiplying it times days, so the days units cancel. So I lost 300 liters of water during the first 12 days. However, from day 12 to day 30, I see that I'm gaining liters of water. So somehow this reserve is being replenished. So now I need to approximate the area under the curve that's on the positive side. So day 12 to day 30. I don't have a very good shape to approximate here. I can't estimate it based on a triangle because I don't really have a triangle here. So I'm going to use a different method to estimate the area above the x-axis. So what I'm going to do is I'm going to look at the area of one block, and then I'm going to estimate how many blocks I think there are here. So I want you to notice that the area of one block, I'm going to make a note over here, one block is 6 units wide and 50 units high, which means each block represents 300 liters of water. So now I have to look at these blocks and try to determine roughly how many there are. So I'm going to start with the whole blocks and I'm going to number them. 1, 2, 3, 4. So there's 4 whole blocks. But then what I need to do is I need to look at how many half blocks and block pieces there are. So I'm going to say that these two together look like they form a 5th block. And then these two together, I don't know how to mark that. Those two together I think would form the 6th block. So I'm going to estimate that there's roughly 6 blocks under the curve. I strongly encourage you to only use whole numbers and half numbers, because if you try to make it more complicated than that, then your approximation is going to get tricky. So if one block is 300 units, and I'm estimating that there's 6 blocks, that means that my area here that I'm approximating is going to be 1,800, because again, that was 6 blocks times 300 units for one block. So that gives me 1,800 liters that seems like they've been refilled into this reservoir. So now I have to put it all together. If I have 1,800 coming in and I have 300 that was going out in the beginning, that means that I'm going to net 1,500. So again, I take my positive area and I add my negative area. So the 1,800 plus negative 300 means that this integral is going to be a total change of 1,500 liters. So I've changed by 1,500 liters and I started with 12,000 liters. So now putting everything together, I'm going to line up my equation here. I have 1,500, which is my integral here, equals Q of 30 minus 12,000. So if I'm solving for Q of 30, the quantity of water on day 30, April 30th, I just need to add the 12,000 over to the left. So again, this matches up directly with my equation. So if I add the 12,000 over, I get Q of 30, 13,500 liters. So again, my graph allowed me to find the area under the curve, the definite integral. And then it was my initial information that allowed me to solve for an exact point. Because I knew how much I started with, I was able to talk about the actual value or the quantity of liters at another given time using the combination of the initial amount and the total change. So let's see how we can put this into practice so that we can actually get lots of values of the original function.